what did we do last time? We did sort of LQR as a QP, quadratic program, saw that. And then we used the block structure in that QP and played this like back substitution game to derive the Riccati recursion. And the sort of big deal there is that it's, number one, it's an order n solution instead of n cubed. So it's really fast to solve, which is super nice. The other big deal is that it gets you, remember this like deterministic optimal control thing we talked about, the answer is a single trajectory, right? But when you do this Riccati thing, you like magically get a feedback policy that's valid for any x. So you get both this like linear time complexity for solving a trajectory optimization problem, and you also get a feedback policy out of this, which is somewhat miraculous. And we'll talk more about that today and hopefully give you like some more background intuition on like what's going on there, why you get the feedback policy, and some other connections. So today we will cover a couple of things. The first one is we're just going to revisit a couple of quick little cleanup things from the LQR discussion from last time. The first one is talking a little bit more about the infinite horizon LQR case, which we kind of saw last time, how for a linear time invariant system, you end up converging to a steady state gain matrix pretty quickly. So we're going to talk about that a little more in detail today. Then we're going to talk about this last piece that came up last time that we kind of glossed over a bit, which is we talked about kind of how, you know, the Q matrix has to be positive semi-definite, the R matrix has to be strictly positive definite to get a well-posed problem. There's also conditions on the A and B matrices, the linear dynamics, called controllability, and that we're going to talk about today, that are required in addition to the Q and R conditions to have a well-posed problem with a unique solution and all that kind of stuff. So we'll do that. So those two things should be pretty quick. And then we're going to get into dynamic programming. Who's heard of this? Pretty much everybody. Cool. This is like a bread and butter computer science thing. So I think the CS people have generally heard about this. If you haven't heard about like, you know, the more dynamics flavored, linear systems flavored stuff, you've probably heard about dynamic programming. So that's cool. All right. This is a fun one. Okay, so let's do just real quick this infinite horizon story. Okay, so we saw last time basically that for a time invariant problem, we saw like empirically that as you go backwards, those K matrices converge to constant values pretty quick. And we talked about some intuition for that, and also said that, you know, in general, for an LTI problem, like the standard approach is to just use that fixed steady state infinite horizon value rather than actually caching like all the Ks for a bunch of time steps, specifically for stabilization problems. So that's like you have a fixed point, you have an equilibrium point that you're just trying to stay on, and you want to just stabilize it. So a good example of that would be a hover for a quadrotor. You want to just stay in one place, or you're moving really slowly about some, you just want to track a reference position, that kind of thing. That's kind of standard. As opposed to a tracking problem, like a trajectory tracking problem, there you generally use a time varying K. You solve a time varying problem, right? Okay, so we have this. Okay, so recalling from last time, it's in the notes, right? We have this backward recursion thing for P, and we're going to talk a lot more about what that means today, but just as a quick aside, we had this sort of thing where we solve for the Ks, and from last time it looks like this. In the time invariant case, so A and B are just fixed matrices, not time indexed. We had this thing, and then we had this thing. And so the idea here is just to look at the recursion and say, in steady state, sort of this infinite horizon limit what that really means here in terms of the recursion is that pk equals pk plus 1. It reaches a steady state, and like k sub k equals k sub k plus 1. It stops changing. So those things are equal. So then we just set them equal, and we now have, so we just take the k and k plus 1 stuff in there, set it equal to just p and k. Now we have a set of algebraic equations we can solve for those infinite horizon values, right? So that's nice and simple. And how might you go about doing that, actually solving that? Anyone have any thoughts? No. It's a, well, okay, so if I just like wrote that down, if I just plug in, you know, P for both of those guys, and move them over, you know, move everything over to the right, say, what that looks like now a root finding problem, right? Okay, so there's two ideas here that come up like based on what we did before. So the one version of this is I just run the recursion backwards for long enough that it converges to steady state, right? And that's what we did last time. Does that look like something we've done before? Fixed point iteration, you got it. So that's a fixed point iteration for P and K. The other way to go, which is the stuff we already did, is I can take the fixed point equations, move everything over to one side and get a root finding problem. And then I can do Newton's method on the root finding problem, right? So it's the same stuff we've been talking about, you know, all along. So those are your options. It turns out because this problem is so common in control theory and shows up so much, people have actually spent quite a lot of effort in like the 70s and 80s figuring out like special, very, very tricky ways of solving this stuff with high precision, blah, blah, blah. So there are like specialized numerical methods, but honestly, not such a big deal. And you can pretty much just do the backward recursion, do the fixed point thing, or you can just plug in and solve with Newton's method. And a really good approach here, if you wanted to do that, remember Newton's method only converges locally, right? So a pretty good approach to doing this, if you wanted to do Newton's method, would be to run the backward recursion for a little while. And then you'd have a really good guess for Newton's method. And then you could basically do 1 or 2 Newton iterations and have like the machine precision answer. Make sense? I should write this down now. So you do this. And we do the stuff we've done before. And then, yeah, the last thing to say about this is Julia/MATLAB/Python all have control toolboxes that will do this for you with specialized methods. It's generally called DARE in Julia and MATLAB. That's coming from MATLAB, but everyone else uses the name now. It stands for discrete algebraic Riccati equation. So you call that function, MATLAB and Julia have it exactly the same way, DARE ABQR, and it gives you that P infinity. And that uses some specialized methods. But you know, in principle, if you had to do this yourself, backward recursion for a little bit, get a good guess, Newton once or twice, you're done. All right, any questions about that? So that's basically the thing to do if you need to just like stabilize a fixed point. And you know, because things are approximately linear in the neighborhood there, this is basically the optimal solution. It's really good. As long as you don't get knocked too far away from that fixed point, really, really good. So things like, again, hovering a quadrotor, balancing some like inverted pendulum thing or whatever, if you're already, you know, at the equilibrium point, this is extremely good and extremely effective. Okay, cool.
Doesn't matter the equilibrium point to be stable or not.
No, yeah, exactly. So in general, you would do this at an unstable equilibrium that you wanted to stabilize, right? So like hovering quadrotor, unstable, wrap it with one of these, stabilizes it. And it actually works for pretty large disturbances. And for small disturbances, this is basically the optimal solution. Because if you're not moving too far away, the linearization is pretty accurate. And then this is the thing to do, right? Okay, cool. Yeah, there's some pretty impressive demos from like a few years ago from Atlas, like Boston Dynamics, where they do LQR with it like standing on one foot like this, and then hit it with the classic, you know, shove the robot thing. It does incredibly well. It just like wiggles around and balances like this on one foot, just LQR in joint space. It's really, really good.
So if you're moving its arm and stuff, doesn't the A matrix change?
Yeah, but you're linearizing it about some pose, right? So if I have a balancing pose like this, it's the same as the homework 1 quadruped balance. In fact, if you want to try this, try it on the 1 foot balancing quadruped. You write that down in joint space. Yes, it's moving around, but like as long as it doesn't move too far, you know, the A is pretty good approximation. And you can like really shove the thing and it will do surprisingly well at balancing. Like it's hard to beat this. Where it breaks down is if you have like, if I had to put my other foot down, then the whole A matrix changes, right? But as long as I can like balance on 1 foot, it's super good. It's like really, really hard to beat. It's quite impressive how well LQR does. For like smooth problems, it's pretty much the thing to do. As long as you, again, don't get knocked too far away from where you linearized. Okay, that's LQR. So now we're going to talk about this idea called controllability. Who's seen this before? Okay, a lot of you guys. Where did you see this before? Okay, you guys, most of you taken a linear systems class. Excellent. This is good. Where is that an ECE here, or where did you take that? ME has one. Okay, good to know. All right. So the kind of basic question here is, how do we know if LQR will work on a given system? This is actually surprisingly subtle. If you're like, remember we said on nonlinear problems, you basically always linearize, you know, in Newton's method, and you get an LQR problem. So one of the tricky things is if you're solving a nonlinear problem iteratively with Newton's method, it's actually very easy to end up with subproblems that aren't controllable when you're linearizing. Like the classic example is if I like have a humanoid and I straighten the knees out, you get singular Jacobians when the knees are straight. That can make you uncontrollable. So like you can have systems where they, for certain values of like the configuration, they become singular and you get like an uncontrollable system sort of instantaneously when you linearize. So this is actually like something that comes up that you have to worry about quite often. Well, no, because there are singular points in the configuration space. So there might be a bunch of these randomly.
Don't go there.
Well, you have to, but you often end up in situations where in the normal course of operation, you have to cross through them. And so like, there's kind of no way around this. Like if I need to go from A to B and in between there's a singular configuration, what do? I can't like get to B without traversing through that, right? So these things can easily become instantaneously uncontrollable. And this is quite common actually. Okay, so this is the question. And well, we're going to talk about the time invariant case because that has a nice clean solution. And I'll like mention briefly what happens in the general case. So we already have this Q and R stuff. So these you get to pick. So there's a fundamental difference here, right? Q and R I just make up. So I can always just pick Q and R that satisfy that. And like I get, that's no problem. The A and B though are not up to us. That's like coming from the robot's mechanics design. I don't get to pick that, right? So these are like subtly different in that respect, right? You gotta, this you can just make up. The other stuff, this stuff you can't choose, right? So we're going to look at the time invariant case. And I'm actually curious for those who how it was done. So here's the way I do it. So for any initial state, x naught, I can write xn as a function of x naught and then all the u's up to that time. And so we'll do that real quick. So what that would look like is xn equals, say, axn minus 1 plus b un minus 1. And then if I were to go back one more time step, I can compose those guys. So that would be a times axn minus 2 plus b un minus 2 plus b un minus 1, right? See where I'm going with it? So I'm basically just going to keep plugging in the dynamics from earlier times in there, and I'm going to get this like recursion thing, right? So what I'm going to do now is just kind of do the ... and then skip ahead. And what you'll end up with if I keep just going backwards like this is the following thing, right? I'll get a to the n times x naught plus a to the n minus 1 b u naught plus say a to the n minus 2 b u1 plus ... And then finally b times u n minus 1. Does that make sense to everybody? Cool. So I go all the way back to time, 0. I get this thing. And I can write this whole thing down as a big matrix equation that looks like this. B, A squared B, ... a to the n minus 1 b. And then this times all the u's. So u n minus 1, u n minus 2, ... all the way back to u naught. So that, and then the right-hand side, and this thing is plus a to the n x naught, right? So x naught is given, it's not a decision variable, right? Cool. So I have now this like little matrix equation for xn. And remember, like, because it's a linear system, and remember what in LQR, we're always trying to drive the system to the origin, right? That's sort of what the cost function is. So what I'm going to do here is, it's sufficient here to just check for xn. I'm just going to check that I can drive xn to 0, to the origin, drive the system to the origin. So again, the goal is to set this equal to 0. So now I have this like matrix equation. And does anyone know like what sort of matrix equation this is? Like what are the dimensions here? Like this is an AX equals B, but for what kind of A and B?
Number of states.
Yeah, exactly. So that the thing on the, it's clearly the output is the number of, it's the state dimension, it's xn, but the x here, this is bad overloading of notation, but that u that I'm trying to solve for is really big, right? So this is a tall, skinny matrix equation, aka a least squares problem. Cool. And so if we remember how to solve least squares problems, it looks like this. We use a pseudo inverse, right? So who knows the pseudo inverse thing? Show of hands. Cool. So if you don't know this, come talk to me after. I think Kevin also talked about this in recitation. So there's a least squares problem for the u's. For u naught to n minus 1. So that looks like, if I were to like try to, invert this thing. We get this equals, and I get this like pseudo inverse thing in here. Oh, I did this wrong. This is for any, this works for any xn actually, but it's enough for me to like get rid of the xn there and put in zeros and whatever. Okay, cool. So this thing, right, is called a pseudo inverse. Okay, so let's talk about now what's a condition on, okay, a couple things. I guess I'm going to call this thing C. So that's what's down there. And that's the thing I have to solve. So in particular here, I need C transpose to be invertible. Can anyone tell me like a condition on, first of all, how big is C transpose dimension-wise? It's the size of X, it's the size of the state. So it's little n by little n. So that's, much smaller than the controls all stacked up there. And what's a condition on, so obviously that thing has to be full rank to be invertible. Can anyone tell me a condition on like the C itself for that to be true?
The rank of C should be the number of states.
Yeah, the rank, I think the same thing. Right? So the rank of C has to be equal to little n, the state dimension, for that to be invertible, right? That's a necessary and sufficient condition. Okay, so let's write that down. We have to have rank C equals little n, where that's dimension x. Does that make sense to everybody? Cool. Okay, so there's one last little trick that we're going to play, and this one's a little more subtle. So I did this, up here for like some arbitrary number of time steps, right? Some like horizon big N. It turns out in the linear time invariant case, I can actually tell there's a specific number big N that I have to go to, and I don't have to go any higher than that. It turns out in the time invariant case. Does anyone know about this trick? Yeah. Cayley-Hamilton theorem. Who knows about that? A lot of you guys. Okay, cool. So, so the deal with that is Cayley-Hamilton theorem says that I can write down any power of a matrix in terms of just the powers up to the dimension of the matrix. That's actually like not the original Cayley-Hamilton. That's a consequence of the original Cayley-Hamilton theorem, which says that every matrix satisfies its own characteristic equation, which is like the eigenvalue equation. But what that tells you is that that's a polynomial of like nth order. And so only matrix powers up to like n, where that's the dimension of the matrix, show up. This is on Wikipedia. You should look this up if this is not clear, but I'll write it down. And we can follow up on this if anybody wants to. So basically, I get to stop at n time steps. Because this Cayley-Hamilton thing says that a to any power, so a to the, say, n, can be written in terms of a linear combination of lower powers. And like an intuitive way to think about this too, in our case, is that adding more powers of A after little n doesn't add any more rank to C. That's sort of the right way to think about it. So here's the kind of key result. It's that A to the n equals sum from k equals 0 to n little n minus 1 of some coefficients alpha times a to the k. So this tells me that like stopping at little n is enough. So to any higher power than that, I've already got like up to that rank. So therefore, adding more time steps doesn't help. And that gives us this sort of final result, which is C equals B A B dot 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 up to a to the n minus 1 B. And this exact thing up to that sort of power is called the controllability matrix. Okay, so anyone have any thoughts on what I do in the time varying case? This is for LTI, where A and B are fixed. How about the linear time varying case? Yeah.
So n here. It needs to be the same number as
The number of time steps I have to take in that horizon of that problem I wrote down is the state dimension. Yep, exactly.
but yeah, what if you stabilize it, limited like economic time stacks. That means you won't be able to cover your entire state.
It means I can't drive the system to the origin in fewer time steps.
To a subset.
Sure, yeah. So that's a slightly different idea. This is called this concept is called invariant subspace. So you can write down like this idea of an invariant subspace and think about like a sort of like n-step invariant subspace. There's like other ideas. That sort of analysis actually is what you have to do in MPC problems with constraints. So linear MPC, this idea comes up a lot. And you think about like subspaces that you can stabilize in certain time horizons given constraints. And in general, they're like for linear systems with linear like bound constraints on the controls, you can write these down as polytopes, and there's like ways to look at that. So yeah, that's a thing when you analyze MPC with a finite horizon and constraints. Okay, time varying case. Any thoughts? What do we do? So what was the only move in here that depended on like it being time invariant?
A and B.
So, well, the only thing I did in this derivation that depended on it being time invariant was really this Cayley-Hamilton move, which was what let me, sort of bound the size of C. If I have a time varying problem, it means A and B are changing, along this horizon. So I can't necessarily make that controllability matrix sort of nice and small, but this result up here still holds. So I can have in this particular setup, if I have a time varying problem that's finite horizon, like a trajectory tracking problem, then I can ask the question, can I drive the error to 0 at the end of that finite horizon? And I can write that down exactly like this. And those A's in there will have subscripts, but this still works. So this result still holds, but this one with down here with the, only little n time steps breaks in the time varying case. Does that make sense? Basically, in the time varying case, in the time invariant case, I can look at just little n time steps. In the time varying case, I have to look at the entire trajectory. Does that make sense? Because I don't have this kind of like nice limiting property, right?
Why don't we just use this if we're, in continuous time, so obviously we can't do this, but since we're working in discrete time, why don't we just use this to find our, mu vector for some finite?
Yeah, so this is like a good sort of thing. This is exactly what, so this is equivalent to an LQR problem with Q and R equal identity, which is not necessarily obvious, but that's, if you work this out a little bit more, that's what this is. But this is like, the caveats here are this version where I've like, basically what I did here was eliminate the X's. So I'm just solving for U. This is sometimes called the condensed form. This is horrible numerically. So you should not do this for an actual control problem. Do you know why it's horrible numerically? Not the inverse. It has to do with that right there. So if A has any kind of ill conditioning, A to the big power n is like whatever the condition number of A was, the condition number of this matrix is going to go like that condition number to the n-1th power, which gets really bad. So if A has condition number, say, I don't know, 10 to the 3rd or 4th, which is not terrible. If it's 10 to the 3rd or 4th to like the 10th power or 100th power, if you're looking over some horizon, that's going to be horrible and your answers will be garbage.
Right, so we have screwed ourselves already in the process step.
Right, exactly. So the reason we don't solve LQR like this is because this is numerically horrible. When you like raise matrices to large powers like that and then need to solve a linear system involving those high powers, really bad idea. So notice the QP version that we set up, that had no higher powers of A, right? Just A's and B's. So that's clean and nice. This has this bad conditioning thing, but this is the classic controllability results. This works fine if you're just checking this version down here in general, because it's small n, right?
You said the dimension of CC comes to this small n cross small n?
Yeah, it's the state dimension. The easy way to see that is the right-hand side here is, A times X naught or whatever. It's size X naught, right?
But if you look at the C value, then it find over, that's like 1 n cross 1, like 1 cross n.
This C here is size like little m times big N, like size of all that stacked, U's, but the output, so the height is the size of X. Right, remember the output of this is supposed to be xn.
Yeah.
Make sense? Cool. Okay. Anything else on this? We good? Yeah.
Now, when you use controllability gramian.
Okay, so that is literally the time varying version. So remember I said in the time varying version, we have to just keep this for all time steps. The controllability gramian is literally, so I said this is controllability matrix. Controllability gramian is just this CC transpose matrix. So controllability gramian is worse again for conditioning reasons because you're squaring the whole thing and it already has high powers of A in it. So gramians are actually horrible to compute numerically and you probably shouldn't do it. But yeah, literally the controllability gramian is the time varying version of this where I take a lot of time steps and then I square the matrix and do CC transpose. Cool. So if anyone's heard of that, that's what that gramian is.
These people that as you have n bases to cover your space, you have actual ring.
I mean, obviously, like CC transpose has to span the state space. And like, that's not a horrible way of thinking about it, I suppose. I don't know. Yeah.
So since all of these approaches are affordable, what do you do in practice if you want to show?
Yeah, so this is okay for this version down here, where it's only up to the nth minus 1 power. As long as n is small-ish, like a small problem, like for a quad rotor or something, this is 12, this is fine.
But I mean for the time.
Time varying case, this is bad numerically. The actual answer to this is you should probably, in practice, right, if you actually want to compute something like this, the real answer is you should just set up the QP and try to solve the QP. That's numerically better than trying to form this gramian thing. And in fact, what this is trying to tell you is if the QP is solvable. So if you can just form the QP and try to solve the QP, this is a better thing to do in the time varying case. Yeah. Okay. Anything else on this? Controllability? Cool. Everyone good? Okay. So that's like kind of the end of our initial foray into LQR. We will now switch gears considerably. We'll still be looking at LQR, but this is like the story from a very different angle. So we're going to now talk about dynamic programming, and this sort of starts with Bellman's principle. Okay, so this is a fun idea. Optimal control problems, as we've kind of already seen lots of hints, have like a very, very sort of particular structure. And this shows up in a lot of ways. One of the ways it shows up is in the block structure of the QP that we saw with LQR, right? It has this very particular block structure, and that let us play this back substitution game to get the Riccati equation. It shows up in lots of other ways, though. And this Bellman's principle is really kind of getting at the heart of that. So kind of the idea here is past control inputs. There's sort of this arrow of time flavor. So past control inputs, only affect the future. And like, you know, this is super obvious and intuitive, right? Like, U's in the future can affect X's in the past, right? So like UN minus 1 can't affect like X naught, stuff like this, right? So it's very, very simple idea. Okay, so that's an obvious statement. Honestly, this is an obvious idea. Like it's very, very straightforward, like intuitive idea. So if you kind of just like take the logical next step from there, this is what Bellman's principle says. So this is also sometimes called the principle of optimality, which I find like sort of very grandiose and hilarious sounding. Here's what it says. I'm going to draw a picture. So if I were to solve like a trajectory optimization problem, like the LQR problem we just saw, and get a solution for like a certain time horizon. So let's, I don't know, like, so this is t, and this is, say x, and I have like x naught over here, and the optimal trajectory, say, wiggles around and like does something like this and ends up at, xn over here, right? And that's, let's say that's optimal with respect to some, cost function, dynamics, whatever. Let's say I took some random xk in the middle of this trajectory, say like right here. And then I like were to resolve this problem, like a shorter version of the same problem, but starting from this xk. The principle of optimality says that this like sub problems solution has to be this sub trajectory from the bigger problem. And the obvious like intuitive thing here is if there were like a more optimal path from xk to xn, like I would have taken that on the larger problem. So it's super obvious result. And like, there's no real deep insight here, but if you just like turn the crank on this and like take it seriously and like look at its repercussions, you can take it sort of far. So I will write this. If this path had lower cost, starting from xk, I would have taken it on the bigger problem. Okay, sort of obvious. And so another way of saying this is sub-trajectories of optimal trajectories have to be optimal for like an appropriately defined sub-problem, right? For like a smaller version of the problem. Okay, any questions about that? I feel like this is fairly straightforward, fairly intuitive. Okay, so here's the math version of that simple story and like where this goes. So now we're going to do dynamic programming. And like the sort of obvious sort of thing that whole Bellman's principle idea suggests is that, if it has this like optimal sub-trajectory idea, the sort of intuitive thing to do then, or what that implies, is that I should start at the end and work backwards, right? So if I start at xn and look like only one time step away, I can solve a little problem, like a little one time step problem, and get the optimal solution. Then I can go back another time step and I can do this sort of backward recursion thing and take advantage of this optimal sub-trajectory problem working backwards from the end, right? So we're going to do that. And I guess the other comment here is we've already kind of seen hints at this when we did Riccati, right? When we did that like back substitution Riccati derivation on the QP, the thing that popped out was that you started at time n and worked your way backwards, right? So hint, hint, this is sort of all connected. We saw this was the punch minimum principal equations, right? So remember the lambda recursion went backwards. The lambda equation went backwards. The x equation with just the dynamics rollout, that went forward. The lambda equation went backwards. And the u calculations that were coming from lambda also went backwards, right? So this shows up in lots of places. And hopefully this whole Bellman story like ties that all together. So I'm gonna like make some stuff up, some notation, and then like this will hopefully make sense as we go. So the first thing we're gonna define is this so-called optimal cost to go. This is also, if you're a machine learning person, RL person, this is called the value function in RL. I find optimal cost to go to be much more descriptive and useful. Value function means basically nothing to me, so whatever. This is, we're going to use the notation V of X for this thing. And what this thing is, in words, is the cost you will incur starting from some X if you act optimally. So this thing tells you like the minimum possible or optimal cost starting at a given state to the end. Does that make sense? Okay. Oh, and yeah, I guess this should have, in general, this is also a function of time, so it's indexed. So if I start at state X at time K, this tells me the minimum cost if I were to like do everything optimally. Okay, so now we're going to do this for LQR because it's our favorite thing. Sorry? No, it's the cost to basically, if I were to solve the entire optimal control problem, starting at state X, this is the cost I would get, right? So if I were to like start at some time K, so in the sub K thing comes from the finite horizon version. So if I have n time steps and I have some state X, if I'm in some state X at time K and I get to like do whatever I do until time N, this is the minimum cost I can achieve. This is like the best I can do if I do everything optimally. Yeah.
Do you have to start from arbitrary? Can you start from arbitrary X, or do you start from like X where you're talking?
So the definition here is this is a function that tells me what the optimal cost is starting from a state X. So it's a function that I can query. Like if I have a given state X that I'm starting at, I plug it in this function, and this function will tell me what the minimum cost I can get is. I mean, the idea is it's a function that maps states into costs, optimal costs, right? Make sense? Okay, cool. So here's how it works. We're going to do this for LQR because that's the one we can solve. And then we'll talk about sort of the more general thing. So this will be very reminiscent of like the other things we have seen. So here's sort of we start at the end. So we're going to start at time N. And can anyone tell me what this will be for like starting at time N for LQR? It's not 0. It's the terminal cost. So I can't do anything else, right? There's no control moves I can make. So the optimal cost at time N, given some state X, is literally just the terminal cost evaluated at X, right? Because I can't do anything else. So for LQR, that's X transpose QN X. And I'm therefore going to define this. So that's just from the definition of LQR, right? That's that terminal cost, terminal state cost. I'm now going to define my cost to go function using this P matrix. And this is going to now hopefully jog your memory and like make you think of other things that we did. So that's it, time N. Now I'm going to do this backwards thing, like we kind of was suggested. We're going to go to time N minus 1 and solve for V N minus 1 now. So let's look at that. So here we go. V N minus 1 of is going to be equal to min over U. And this is UN minus 1 to be clear, right? It's just the one-time step. I have only one control move I can make, right? It's the last time step before the goal. And so the thing that shows up then is the one step cost from time n minus 1. So that's the state cost, the control cost. And then I have the terminal cost, which I'm going to write like this. So Vn with the dynamics plugged in so that everything is evaluated at time n minus 1. Everyone cool with that? Back up one time step. So now I'm just going to crank through and compute this thing. So I will plug in my definition of Vn minus 1 now. And that's going to look like, so the first thing is I'm doing min over u. So that xn minus 1 term in front there drops out. It doesn't matter, right? I'm taking the min, so because it doesn't affect the min, so I can drop that term. So I get just this guy. And then I'm going to plug in the dynamics and into like my actual Vn minus 1 there. So it's going to look like this. And I'll be a little loose with the notation and stop writing all the time subscripts because it's annoying. But it's sort of, this works in, time varying, kind of all the cases. Okay, so there's that. And now, yeah.
What does it capture how far it is from the goal? Like,
so we're going to just keep going backward. And you'll actually get Vn minus 1, Vn minus 2, Vn minus 3 for all time steps.
but time step can like go backwards, but it might be still close to the goal or far from the goal. How does it track?
In terms of where the state is.
Yeah.
So what we're going to get out of this is Vn minus 1 of x. It's a function of x. So we plug in whatever x we're at that time, and it's yeah. So we'll see that in one sec here. So what kind of function is this of u? Quadratic. And based on all our sort of positive definite blah blah blah, it turns out it's positive definite also. So I can solve this min by just taking gradient equal to 0. So let's do that. I will then get, if I take the gradient of that thing and set it equal to 0, I get the following. And what I did here is set grad u equal to 0. Cool. And so then I can solve this guy for un minus 1 explicitly, the optimal un minus 1, and it's this thing. I'll put the time scripts back in there now. This should be transpose. Okay, that's kind of a lot, but that's it. And then what do we think of this thing is? Based on last time, this thing? Yeah. So this is basically going to give us the Riccati equation again from another perspective. This thing is the K matrix, the feedback gain from that we saw last time, right? And then what we're going to do now to get the Vn minus 1 is we're going to take this K, which tells us the U as a function of X, right? So I eliminate the U. So I can plug this feedback policy back into this equation up here, which will eliminate all the U's and tell me what Vn minus 1 is as a function of X. Cool. So let me write that down. Plug U equals minus KX back into this starred guy up here. And I get now Vn minus 1 of X equals 1/2. Oh, I should write this all out. If I expand this out, I get 1/2 X transpose, and then this big mess that I will write out. Again, I'm being a little loose with the subscripts, but it should be obvious what they are. So you have to go back in and figure them out. this thing times x, and this thing in the bracket is Pn minus 1. So we've now got this like backward recursion for k and p. And I can rewrite this guy as v n minus 1 of x equals 1/2 x transpose p n minus 1 x. And now I have the recipe to compute the p's and k's all the way back and kind of keep going. And the kind of key thing that lets me do this is in the LQR case, the cost to go function stays quadratic. So I can write it down as just this p matrix, this like, you know, matrix in the quadratic form there. Okay. So this looks, you know, very much like the Riccati thing we got before, just looking at the QP. It makes it a little more explicit, like where this feedback policy thing is coming from. And it looks a little different though, right? Does anyone notice a difference between this and what we got last time? So in general, we'll iterate this backwards until k equals 0. And this is the Riccati equation again. It is a little bit different. The k equation is exactly the same as the one we got last time for Riccati. The p equation is a little bit different. And in particular, this p is symmetric. If you notice like the way it's all set up, every single term in that sum is symmetric. The version we got last time isn't. But p is supposed to be symmetric because it's a quadratic form. So if you're doing this numerically on your computer, this is the better one to use because this one guarantees symmetry of the solution. It also guarantees positive definiteness, right? Because all those terms are added together and they're all symmetric. So numerically, with like floating point round off and stuff, this is the better one. It turns out there's like multiple ways you can write this equation for p. It's a handful of different versions. And like from a numerical perspective, floating point perspective, this is probably the best choice. Yeah.
You still get the same quadratic form, right? It's the same.
Yep, you'll get the, so in infinite precision, they are exactly the same. Like linear algebra wise, you can like get the other one from the other. It's just like some matrix manipulation, but this one is better from a floating point error perspective. So if you're doing this on a computer, this is the better choice. Okay. Any questions about this?
All depends on Q and R, like Q being semi-positive and definite. And
Yeah, so as long as Q's, sorry?
How do we choose those?
Yeah, so that's what you get to pick. As like a engineer, those Q and R values are what shapes the behavior. That's what you get to choose to like, that's the cost function, right? That's like what you're asking for. Yeah, there are. So we'll talk about this a little bit. There's a couple of like, you know, rules of thumb like for this. But in general, like those are the knobs you have to turn to like tune the performance of the system. If you've done like classical CISO control, you remember like there's these rules for like gain tuning, and you can ask for like different, you know, overshoot and steady state error and how fast it responds and stuff like this. It's kind of a similar vibe. Here, the Q and R are the knobs you can turn instead of just the gains directly. And, you know, intuitively, if I increase Q and, you know, that's saying I care a lot about driving the state to error down fast. If I like, you know, if I make Q bigger and R smaller, it says, you know, push really hard, get it to the, you know, so you'll get generally like faster response. If I go the other way and make Q small and R big, it says I want to penalize the control effort a lot and I care less about the state error. So it'll respond slower and whatever. That's basically it. The other thing is the absolute values of Q and R are not what matters. It's the relative scaling between them. So it's always like how big is Q relative to R and vice versa that actually matters. If I increase them both by the same factor, like if I jack both up by a factor of 10, say, I get the same answer because it, you know, it's invariant. I can divide the whole cost function out by that and it doesn't change anything, right? Cool. All right. So let me write down then like the general form of this dynamic programming idea. So here's the general case, right? Not the LQR case. It looks like I start with this guy just being the terminal cost. And then I say, set, you know, k equal to n, and then I go backwards. So I'll write this as like a while loop I get Vn minus 1 by solving min over u for u within some feasible set, right? So it could be bounds or whatever. And I solve the one-step cost plus the cost to go at, oh, this should be k, sorry. So this is vk minus 1, and this is vk. And then I plug in the dynamics, right? So this is the general nonlinear case. So I solve that problem, and then, you know, decrement k, and keep going. And then, so there's a sense in which, like, if I know this optimal cost to go, this v, I know everything about the solution to the optimal control problem. If I have that, it's almost as good as having the optimal feedback policy, because that kind of gives it to you. If we know, the V's, the optimal policy is just u k of x equals arg min over u. I just plug in my current state to this guy, and I solve this guy with respect to u. So that's like, I can just solve this little sort of only dimension of the one control input at the one time step optimization problem. I plug in the x there, solve that for u, and that gives me the optimal feedback policy, right? Yeah.
In terminal cost, it shouldn't be zero, like you say, reach the goal. It should be not penalized anything.
No, if we're at the goal, it's 0, right?
Yeah.
But if I'm not at the goal, that's what cost I get.
So,
If I'm off, I have this terminal cost, right? Like in the LQR definition,
so it
or
would be x minus xm, like instead of xm.
so in LQR, the goal is to get to the origin. If I'm at the origin at time n, cost is 0. The cost to go 0, terminal cost is 0. If I'm not at the origin, I get cost, x transpose qn x.
So we are assuming xn equal to 0.
In the LQR problem, we're assuming that the goal state is 0. If I have another goal, then it would be, x minus x goal transpose, whatever. And you can absolutely do that, and that's fine. But in the just standard vanilla LQR problem, the goal is always the origin. So if you're not at the origin, you get that cost. Yeah. Okay, cool. So this is the general case, nonlinear, et cetera. Yeah. Sorry, can
How do we go about obtaining this optimal people?
like this. That's it. That's the definition, right? So I start at Vn. I know Vn from the terminal cost, just that I make up. And then I can bootstrap and I can go backwards in principle, right? And do this. Solve these little one-step optimizations, right? To get all the way back. But here's where, okay, so this is good to know. There's one other little thing we should talk about, which if you're an RL person, you will know about this. So I can equivalently write this stuff in terms of this other thing called the action value function, or also called Q function. Who's heard of this? Okay, only about half of you. So what this thing is if I were to, so we're going to call it S because we're already using Q for LQR stuff. But normally, if you were to take like an RL course, this would be called Q. And this thing, remember the V is a function of just of X. The action value function is a function of both X and U. And it's defined as the following thing. So it's literally just the whole like thing that I minimize in the backward recursion. So it's the one-step cost plus the value function with the dynamics plugged in. So it's like just the value function composed with the dynamics and the one-step cost all put together. And so given this thing, I would get, it simplifies this down to just be, arg min over U of S. So why might I do this? Why would I like to have this S instead of the V? Why do we do it in RL? Anyone know?
Visualization functions there, because you don't have closed forward energy.
It's exactly the same, actually. So the reason we do this is so I don't need the F. So like if I have the V and I want to go solve this like problem online, I need to have the dynamics model F to like plug in, right? If I instead get this, compute this action value thing, it's basically got the F buried inside it, like implicitly. So when I go online, I just need the S. I don't need to like have access to the F, the dynamics model at all. So if you're doing model-free RL, this lets you, in principle, do a bunch of like sampling, whatever, and experiments and compute this S thing without ever needing to know F. Whereas the classical version that we did with the value function, I need to know the F sort of to get the V thing to work out, right? Does that make sense? This is like a model-free kind of idea. Cool. So usually this is called Q. We will see this again in the future, and it's going to be S for us. But there's too much notation overloading, and I couldn't come up with a better thing. And this, yeah, the whole reason to do this is it avoids needing the model. Assuming you can do lots and lots of rollouts on your system, on your hardware system, which is not generally true in practice. And so people do this in simulation, but your simulator is the F. So if you're doing RL in a simulator, questionable, in my opinion. But other people disagree with this. Okay, so so now we get to talk about the curse, the famous curse. So this dynamic programming thing seems, seems awesome. Seems like it solves all our problems, and like we should just be able to do this and get this value function thing, and life is good, and I can solve any control problem I want. There's some other really amazing things about this. So this dynamic programming thing I just wrote down with this whole value function, it turns out this is a sufficient condition for a global optimum. So if I can do dynamic programming and get this V, I'm done. I know everything there is to know about the problem. I've solved for like the globally optimal solution. It's like the best thing ever. So why don't we do this all the time? Who knows this? Who knows about the curse? Yeah. So what's this really getting at, though? That's the right thing. Like, can anyone like give me some intuitive explanation of what the curse is? Like, why don't I just do this for everything?
There's so many states.
Yeah. So the real reason. So these are all like, part of the story. So this is only tractable for basically for easy problems, for LQR and a couple other simple problems. And what happens in the general case is that it might be buried in your previous question, like for anything non-linear is I can't actually write down V of X. So remember, V of X is a function. So in this like backward thing, I'm solving for a function. And in general, like, that can be arbitrarily complicated and weird and nasty and doesn't have any kind of closed form. We get lucky in the LQR case because V stays quadratic. And for a quadratic function, I can write it down in like very simple terms as a matrix, basically. But in the general case, it does not stay quadratic. Even if I have a quadratic cost, right? As soon as I write down a nonlinear F, remember in this problem, like I have to compose V with the dynamics function F. So if F is linear, great. Quadratic, linear, I get a new quadratic, right? I smush all the matrices together, get these quadratic form things. But if F is nonlinear, all bets are off. And this can be like arbitrarily crazy and like impossible to write down in any kind of closed form. Okay, so that is the real, that's the real reason is I can't write down V. in any nice way for a general nonlinear problem. This issue is a little more obvious if you do this in continuous time. In discrete time, we get this like recursion, like we saw. In continuous time, does anyone know what the Bellman equation looks like? This backward recursion thing is called the Bellman equation. Yeah. No. The least action thing is Pontryagin. It's a different beast. So yeah, Hamilton-Jacobi-Bellman, which is a partial differential equation. It's a PDE in the state dimension, and it's a nonlinear PDE. So for the Mecchi types who know about PDEs and have maybe seen like Navier-Stokes and things like this, it's worse than Navier-Stokes. It's a nonlinear PDE because Navier-Stokes is only in 3D. This is a nonlinear PDE, so like in principle as nasty as Navier-Stokes in terms of the kind of equation it is, but it's in the state space of your robot. So it's a nasty nonlinear PDE and potentially like 100-dimensional state space if you have like a humanoid robot or something. So it's like if you think about how hard Navier-Stokes is, that's only 3D. This is that sort of flavor of bad, but in like 50 dimensions, whatever the state space is. So like absolutely horrible, and that's really the heart of it. It's this. We don't know how to solve that sort of thing, right? Yeah. So I wrote it as x without the subscript because the idea is it's v sub k. So the function is indexed in time, but like we're just plugging whatever x we're at into that. Does that sort of make sense? Okay, so that's this story. And then the other sort of so that's the real reason. The other sort of side comment is that even if we could do it, even if we could get the V, the one-step online problem to get the feedback policy, in the general case, that would be a non-convex problem, which is also potentially nasty. So this guy will be kind of hard also. Okay, so why do we bother with this? Yeah, cost of DP blows up with the state dimension. That's the curse of dimensionality. And the sort of obvious reason is that in general, if we're talking about solving this thing and representing that function, like the only general way to do that would be to like grid the state space. And like the number of grid cells you get blows up like exponentially with the state dimension. Okay, so why bother? Anyone have any thoughts? So anyone? Nobody. Okay, so okay, so here's why this whole thing is useful. Approximate dynamic programming, where we start to use function approximators for the value function or action value function, that's the basis for tons of things. That is the basis for like all kinds of modern RL algorithms, right? Use a deep neural network for V or S, you have deep RL. And it also is super useful in model predictive control. It's also one of like the key ideas behind MPC, which we're going to see like in the next couple of lectures. So that's one. And then the other idea that is very powerful is that so V or S. So that's one idea. The other key idea is that DP generalizes to stochastic optimal control problems where Pontryagin stuff does not. So this is like the road to stochastic things and lots of interesting problems that like doesn't sort of carry over otherwise. Okay, so that stuff, and we're out of time, unfortunately, because of my stupid iPad challenges in the beginning, but I'll hang out for a bit and I was also going to tell you what the Lagrange multipliers mean. So we'll have to do that next time. That's the teaser to leave you hanging for more. What are the Lagrange multipliers from the QP / the, the LQR thing? That came up a lot. So I wasn't going to do it today, but we ran out of time. So next time I'll tell you what the Lagrange multipliers mean.